This is also called a quantitative electroscope. I had these when I first started teaching. I bought a bunch of them and they sucked. So basically a quantitative electroscope has a little gauge on the side where it turns based on how much charge it has, and they never work. So when I came here, I bought the old electroscopes. Lightning!
Okay.
Pika, pika.
Okay. So, lightning. Oh, by the way, that's a pika. A pika is like a little rodent. They actually exist. Anyway, so what happens in lightning? Here's the crazy thing about lightning. It's been going on since the beginning of time, and we don't really know exactly why it does it, but we have some guesses. And here's our best guess. When there is lots of clouds, some of those clouds will have a charge separation because as pressure increases in the atmosphere, decreases under the atmosphere, increases in the cloud, ice will form and ice will fall through the clouds, creating a charge in the cloud. It's that first part we're not sure about. The second part we're pretty sure about. So we think friction in the air as ice travels through the cloud creates a negative charge in the bottom of the clouds. This is the cloud. Okay. Now clouds are really big. If you have a big negative charge here, what happens down here?
Yeah.
A positive charge is formed. So the big negative charge causes a positive charge to be polarized in the giant metal globe that we call the Earth. The Earth is a giant metal globe.
Why is it that?
I don't know, that's the way God made it. It's nickel and iron in the middle, and then silicon dioxide are on the outside. So it's metalloid on top of metal. So
Wait, so
dirt's mostly metal, yeah. Dirt's mostly metal. It's iron and copper and zinc and calcium, and with a bunch of oxygen in there too. But yeah, Earth is a big ball of iron and nickel, surrounded by a bigger ball of iron and nickel that's metal, surrounded by a bunch of oxides, so mostly iron oxide, nickel oxide, copper oxide, zinc oxide, a little bit of silicon oxide in there too, but mostly metal. All right, so you got a big charge, negative charge, positive charge, and when you have a big charge, what do you get? If the charge is bigger, listen carefully, if the charge buildup is bigger than the insulator in the material, then you get a lightning bolt. Okay? When the charge separation is bigger than the insulator, you get a lightning bolt. And the insulator has a name. And I don't know why it's called this. It's called the dielectric. Di. The insulator in the middle is called the dielectric. Maybe two poles? The thing between two poles? I don't know why it's called dielectric. But the insulator in between the materials is called the dielectric. So when the charge buildup is bigger than the strength of the dielectric, that's when you get a shock.
Basically, the charge overflows and has to go somewhere.
Exactly. The charge wants to re-neutralize the material. Charged materials are unstable. The charged materials want to neutralize themselves, and the point at which those charged materials are charged up enough to cause a lightning bolt to go through the dielectric, and that's what happens.
What was that?
The dielectric?
No, the insulator.
The insulator is called the dielectric.
The thing where the charge is held until it overflows.
Oh, capacitor. Yeah, we'll talk about that tomorrow. We'll talk about that next time. Yeah, we're just planting the seed. The dielectric is one of the words you're going to need when we talk about capacitors. Okay, so moving on. Coulomb's law. Hey, there's math, of course. Coulomb's law is just like universal gravity, where you have two objects with mass, Lane and Bowen. You have two objects with mass that are attracted to each other. Two charged particles, or so two things that are statically charged, will be attracted or repelled based on their charge and the square of the distance between them. Sorry, was that too fast? Okay. So, standard unit of charge is called the Coulomb. The Coulomb is the charge packet of 6.25 times 10 to the 18th electrons. I'm not going to tell you why that number is significant, but it's significant. You can just realize that the Coulomb is the standard unit of charge. So the force of attraction or repulsion between two charged objects is equal to the charge of the first object multiplied by the charge of the second object divided by the square of the distance between their centers multiplied by Coulomb's constant, which is 9e9. Not here somewhere. Where is Coulomb's constant? Here we go. Coulomb's constant is 9 times 10 to the 9th, which is pretty cool. 9 times 10 to the 9th. Hey, Carson.
Hey, this is what's in the quarter.
Cool. Hand and key. Yeah, I nominated him, but he isn't. But Chris Mullen can go for it. Somebody should go for it. Does anyone want to? Is Lana going to be back tomorrow? Probably not.
What did they get nominated for?
Student of the quarter. Who wants to go as Landon?
I want to go as Landon.
Okay.
Oh.
There you go.
I'm Landon's representative. Yeah.
Accepting on behalf of Landon is Emily.
He asked me to get into the same.
Yeah. You can just like, I'm accepting his award on his behalf as he's doing the hula dance. Okay, so that's force. Now the force is in newtons because all force is in newtons. And Q, Q, D squared, and that's Coulomb's law. Now, question.
In the formula, can we change it to C instead of K to help convert? Or is that like pretty bad?
I wouldn't, because the units of coulombs are going to be in capital C. So the variable for charge is a Q. The unit for Coulomb is a C. And by the way, you're going to see capital Q and lowercase q all the time. Okay? You're going to see a capital Q or a lowercase q. They're used almost interchangeably. What you usually see is you see a capital Q when you have multiple charges and a lowercase q when you have a point charge or a sample charge. Does that make sense? So usually capital Q is used for charges moving and lowercase q is used for charges that are fixed in place. But not always. Some internet authors, some teachers and professors, some textbooks, they use capital Q and lowercase q interchangeably. But by convention, big Q, flowing charge. Little q, charge fixed in place. All right, any questions about Coulomb's constant? All right, is Coulomb's constant really big? 9 times 10 to the 9th. Yes, it's huge. Coulomb's constant is enormous. It's 9 times 10 to the 9th. It's 9 billion. It's a very, very big charge, or it's a very, very big constant. So what this means is you can have itty bitty 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 charges in Q and Q1, and distance between them irrelevant, producing a pretty large force, which is why the balloon will sometimes stick to you. Okay, moving on. We're gonna get to that next. That you don't even need. Okay, fields. Now, when charges are fixed in place, they create electric fields around them. And fields create field lines to tell the viewer what kind of field you're dealing with. Okay? Point charges create fields. A negative charge will create a field that points towards it. Okay? Once again, charges move from the positive to the negative. Okay? We consider positive to be high potential. We consider negative to be low potential. Things naturally want to move towards low potential. Make sense? So by convention, a point charge that is negative will create an inward field, and a point charge that is positive will create an outward field. We draw these fields with 8 lines, usually on the axes and then at 45 degrees. That's just by convention how we show them. I can't believe it. Thing's still going. Still going at 15 minutes of charge. Way to go, GoPro. I take everything about you that I said about you.
Guys, and once I
Not everything,
I was
no.
like-
It's still a piece of junk. Okay, now, if I drop in a point charge in this positive field, if the point charge is negative, what's it going to do? It's going to go towards it. If the point charge is positive, what's it going to do? It's going to move away from it. It's going to accelerate away from it or accelerate towards it, right? What do you need to produce an acceleration? A force. And this is how you get it. The force of any test particle put in a field is simply the product of that force or that test charge multiplied by the field strength. Now, I mentioned there's a lot of analogs between gravity and electrostatics. Can you think of how this might be an analog to gravity? Q is equivalent to mass.
Oh, I thought that meant force of gravity.
Exactly. So you could basically say this is very similar to Fg equals mg. When you put a mass in a gravitational field, it feels, this is a small g by the way, F sub g. When you put a mass in a gravitational field, it feels a gravitational force. Make sense? So when you put a test charge in an electric field, it feels an electrostatic force. Do the fields lab with it tomorrow. Yeah, the PhET simulation has an excellent, one of the best representations of charges in fields that I've ever seen. It's really great. Okay, that's it. Similarly, a negative charge creates a negative electric field. So if a negative charge creates an electric field, it's an inward field. Okay. And then you put a charge in there, and there you go. Okay. If you double the charge, how does the force change? Twice as much, right? So if you double Q, your force is going to be twice as much. Now, just like we assume that we're all near the planet, and G is always about 9.8 or 10 if you're near the surface of the planet, we're going to assume that you're near the effective field. Okay? If you got really far away from the planet, your gravitational field is going to shrink, right? Same thing happens with electric fields, which is why the next unit is, or the next formula is important. Are we ready to move on? Probably not going to finish today, but that's okay. Okay, so you take Coulomb's law, which is F equals K Q1 Q2 over D squared, and you realize that F is also QE. And putting these two things together, you can do a little systems of equations if you like, or you can just substitute that QE is equal to F, so QE equals F Q1 Q2 over D squared. Q1 is what's producing it. You cancel out Q1, and you get this formula. Electric field, this is with the actual electric field strength, is given by Coulomb's constant times the charge of the field that created it multiplied by how far you are away from your test charge. Basically, how far you are away from the center of that charge. This is how you can tell this is how strong a field this test charge creates. But you need to know how far you are away. So, can you measure the field on the test charge? If you had a test charge and you put your sensor right on top of the test charge, can you measure its field strength? So this is my charged, this one. This is my charged object. It's radiating an electric field. let's say it's a positively charged object. It's radiating an outward field. And I take my test probe and I'm like, what is your field? Can I determine what its electric field is at the point charge? Why not?
Because D is 0.
Because D becomes 0. But, as you look, exactly, this is important. You can't determine the field strength at the charge itself. But, as you go away, and you get a D, you can say, all right, I know your test charge quantity. I know how far you are away. I know what Coulomb's constant is, 9 times 10 to the 9th, 99. Then I can figure out what is the electric field here. What is the electric field here? What is the electric field here? And then if I know that, I can drop a test charge in, multiply the quantity by the test charge by the electric field, and figure out what the strength of attraction or repulsion is for that test charge. Does that idea make sense? Okay. Kind of mentally abstract. I'll go over it again. Yeah.
Is E equal to the field strength? Is that what that
Yes.
is? Okay.
Capital E is the field strength. And the unit is kind of interesting of E. We're going to give a new unit next week, but right now, force is newtons and Q is coulombs. So what do you think the unit of E is? It has to make everything, all the units have to cancel out. Close. Newton per Coulomb, yeah. So this is Newton per Coulomb. Okay. All the units have to cancel out. So the unit of field strength is Newton per Coulomb. Yeah.
And since it's just distance, orientation in the electric field doesn't matter, right?
Correct. Yeah. Point charges, we just assume that they're there. They don't aim in any direction. And similarly, a point charge that creates a field radiates in all 3 dimensions uniformly. Okay, so once again, if I have my point charge and I'm going to put into it a test charge, I need to know, like I'm going to put the test charge right there. I need to know what the electric field is at that point. So I take my test charge quantity and I multiply it by K, then I divide it by the square of the distance. That gives me the electric field right here. Once I know my electric field, I can multiply that electric field by the test charge's quantity to find out what force it would have of attraction or repulsion. Capiche? Okay. Yay, electrostatics. Think. Let's see what's left. Potential. Oh wait, okay. Yeah, let's talk about potential. The bell's gonna ring in my minute. Okay. So a ball in a gravitational field has the potential to fall, right? This ball has the potential to fall in the gravitational field. By falling through the gravitational field, its potential energy does what? It decreases. High potential energy, low potential energy. Potential to fall, no more potential to fall. A test charge does the exact same thing. When you put a test charge in an electric field, it has the potential to move towards or away from that field. How much energy it has is... Oh, we're not at energy yet. Never mind about energy. We're at potential. V is the electric potential given in volts. Okay. We'll come back to this tomorrow. Wow, the GoPro lasted all that time.